In this video, we are going to talk about reduction of alkenes and alkynes. So one of the ways to reduce an alkene is use of catalytic hydrogenation. So during the hydrogenation process, we are going to add molecular hydrogen across the double bond. Therefore, we are going to convert an alkene to alkane in this process. So we are going to add each hydrogen to each carbon of the double bond. Now, to perform this reaction, we need a metal catalyst. And the metal that we can use for this reaction can be palladium, or platinum, or nickel. So with either of them, we can perform this reaction. Now, regarding the stereochemistry of the hydrogenation reaction, so as I mentioned, each hydrogen will be added across the double bond, and they both will be added from the same side. Therefore, addition here is seen. And if you are forming a chirality center in the product, you need to think about stereochemistry and show the stereochemistry. So in this example, none of these carbons is chirality center. Therefore, we don't need to show the stereochemistry. Now, let's look at the first example. So I need to add molecular hydrogen across the double bond. Okay. Now, do I need to show the stereochemistry here? Yes, because this carbon and this carbon, both of them are chirality centers. So I need to show the stereochemistry. Now, if the molecular hydrogen added to the double bond from the top, we can show both hydrogens in wedge and the other groups that are connected in dash. Now, if the molecular hydrogen get added to the double bond from the bottom, we are going to form the enantiomer for this molecule. So we need to show both hydrogens in dash. So the important point here is that both hydrogens are added across the double bond from the same side. So we need to show the addition is happening through syn process. And once again, if you are forming a chirality center, don't forget to show the enantiomer as well. Now let's look at the second example. So in the second example, again, we need to add molecular hydrogen across the double bond, and after doing this, we are going to form two chirality centers. So we need to show the stereochemistry. Okay. Now, do I need to show the enantiomer here? No, because this molecule is a meso compound. So it has plane of symmetry. And if you remember, we cannot draw an enantiomer for a meso compound. So when we have symmetrical alkene, we will form a meso product. So we are going to form only one product, which is a meso compound, so we cannot show the enantiomer for that. This slide will explain why addition of molecular hydrogen across the double bond is happening through syn addition. So in catalytic hydrogenation, you have a metal surface. Now, when the hydrogen gas bubbles in, the hydrogen gas is adsorbed on the metal surface. So pay attention, it is not absorption, it is adsorption. So this process causes breaking hydrogen-hydrogen bonds and forming individual hydrogens on the surface of the metal. Now upon that, when alkene comes in and coordinates to the surface of the metal from its top or bottom face, each hydrogen is added to each carbon of the double bond to the same face that alkene coordinates to the surface of the metal. So that can explain why addition is happening through syn process. The catalysts that we talked about till now for hydrogenation, such as platinum, palladium, or nickel, they are called heterogeneous catalysts because they don't dissolve in the reaction media. They are solid metals, and they are not dissolving in the solvents of the reaction. However, the hydrogenation can also be done using a homogeneous catalyst, which is soluble in the reaction solvent, and that catalyst we call that Wilkinson's catalyst. So this is a pretty large catalyst. Of course, you don't need to know the structure of that. However, you need to know the product of its reaction, which is exact the same as what we just talked about. So again, we have syn addition of hydrogens across the double bond, and if we form a chirality center, we need to show the stereochemistry using wedges and dashes. So for example, for this specific example, we are going to have addition of 2 hydrogens across the double bond. So we have syn addition. If addition happens from the top, hydrogens will be in wedge. And of course, we are going to make the enantiomer for this as well. So it's exact the same as what we just talked about, but the catalyst is soluble in the reaction solvent. Now let's look at reduction of an alkyne. So there are a few ways that can help us to reduce an alkyne. The first one is catalytic hydrogenation. So in this reaction, same as alkene, we are going to use hydrogen molecule and some sort of metal catalyst such as platinum, and we are going to convert the starting material, which is an alkyne, all the way to alkane. Now the mechanism for this reaction is exact the same as surface reaction that happened for alkene, and we are going to have syn addition here. Now let's see what's happening in this mechanism. So what's happening here, we are going to reduce the alkyne to the cis alkene first, because addition is syn, so we are going to form a cis alkene, and then we are going to reduce the alkene all the way to alkane. So this reaction basically goes through this intermediate, which is an alkene. However, we cannot isolate this intermediate. So it is almost impossible to isolate this intermediate. So whenever you have an alkyne and hydrogen molecule with some sort of metal, such as platinum, palladium, or nickel, you are going to reduce that alkyne all the way to alkane. You cannot stop the reaction and isolate the alkene. Now, if we want to stop hydrogenation at the alkene, we use a catalyst called poison catalyst. So the mechanism is still a surface reaction, but instead we are using a different catalyst, which we call Lenzler catalyst. So as you can see in this catalyst, we still have the metal, so the mechanism is still a surface reaction, and we call that poison catalyst because it is not as reductive as hydrogen, palladium, or platinum, or nickel. So you don't need to know the details for this catalyst and the structure for that, but you need to know the product of its reaction. So let's look at this example. So if we have an alkyne such as this, and it reacts with Lindlar's catalyst, we are going to form an alkene. Now what type of alkene? we are going to form a cis alkane. So the product for that would be cis alkane, because as I said, the mechanism is still similar to the hydrogen palladium or platinum mechanism. So we are going to add hydrogen molecule across the double bond through syn addition. So addition is still syn, and we are going to form cis alkene. So another important thing, don't forget that the double bond is planar. So to show the stereochemistry, we are not using dash and wedge bonds. So as long as both hydrogens are on the same side across the double bond, that means the addition is syn, and we are going to form a cis alkene. The third way to reduce an alkyne is through dissolving metal reduction, and we will form a trans alkane here. So we are going to use sodium and ammonia as reagents here, and we are going to form a trans alkene as I mentioned. So the mechanism for this reaction is through formation of radicals, and we know that radicals are forming through homolytic cleavage. This is going to be the only radical reaction that we are going to discuss in CHE230. So in radical reactions, we are using one-sided arrow, if you remember, because it involves homolytic cleavage. So this is the one-sided arrow. It shows movement of a single electron in the mechanism. Now, the first part of this mechanism involves formation of radical, and the next part will form ionic product. If you look at periodic table, how many valence electrons sodium has? 1. So when sodium dissolves in ammonia, it will serve as a source of electron. So what will happen is that sodium forms the sodium ion and electron. So we are going to use that single electron to start the mechanism for this reaction. So the first step of this mechanism is a radical reaction. So what's happening? We have an alkyne. So one of the pi bonds in alkyne breaks homolytically. Okay, so one electron transfers over this carbon, and the other one will be transferred over the opposite carbon. And also we have sodium in the solution, so sodium will also donate one electron. So it doesn't matter which side take the electron from the sodium, the result would be formation of this radical anion. So we still have one double bond left. This carbon takes one electron, so forms the radical, and this carbon has two electrons, so it will form the anion. So this species, this intermediate, is a radical anion. Now the anionic part of this molecule can act as a base, and we have ammonia in the solution. Ammonia is our solvent, and it's a good source of proton. So it will take the proton from the ammonia. So this step is a proton transfer step, and forms this radical. Now we still have sodium in the solution, so again sodium donates one electron to the radical to form this anion. Okay. Now again, in the last step, this anion will act as a base and takes the proton from the ammonia. So the last step is a proton transfer step. to form the trans alkene. So we have a pattern here. So the first step is the electron transfer step, and in this step we are going to use only one-sided arrows, so fishhook arrows in this step. The second step is a proton transfer step, and in this proton transfer step we are using two-sided arrows, so the normal arrows that we were using for acid and base reactions. Again, the third step is an electron transfer step. Again, we are going to use one-sided arrow, and the fourth step is the proton transfer step. And we are going to use our normal acid and base reactions curved arrows. Now, why do we specifically see formation of transalkenes but not cis alkenes? So the intermediate for this reaction was the radical anion. Now, if the radical anion want to be in the cis format, which is this molecule, the single electron and a lone pair of electrons, they would experience a large repulsion. Therefore, this molecule would be higher in energy and basically less stable. So what will happen, the orbitals would rather to be in the opposite sides to reduce the electron repulsion. So this intermediate would be lower in energy and more stable. So the reaction proceeds through the lower energy intermediate and forms the transalkene. This slide is just the summary of what we talked about reduction of alkynes. So if you want to form an alkane out of alkyne, you need to treat the alkyne with hydrogen in the presence of one of the metal catalysts such as palladium, platinum, or nickel. Now if you want to form a cis alkene out of the alkyne, so this is the cis alkene. So we have the cis alkene here. We need to treat the alkyne with hydrogen in the presence of poison catalysts such as Lindlar's catalyst. Now if you want to form a transalkene, so this one is a transalkene, we need to treat the alkyne with sodium and ammonia.